Okay, so now continuity and differentiability. So the definition of continuity is that the limit as x tends towards a of f of x equals f of a. Okay, so now this is a short statement, but there's a lot that goes into this statement, meaning that the limit as x tends towards a from the left has to equal the limit as x tends towards a from the right, hence that the limit itself has to exist. So, and it has to actually equal the function value at that point, right? Now, differentiability, which is actually a stronger condition for a problem, asks that the derivative at that point has to exist, meaning that we can calculate the slope of the function at that point, okay? So differentiability is a stronger condition than continuity. So we have this theorem right here, this statement. So if f of x is differentiable at a point, then it is continuous at that point. Okay, now what do I mean by the concept of differentiability is a stronger condition than continuity, okay? The converse is not true, okay? So when talking about the concept of which condition is stronger, if a function is differential at a point, then it has to be continuous at that point, okay? By saying the converse is not true, what that means is that just because a function is continuous at a point, that does not mean that it is differentiable at that point. Okay, so we'll start out with one of the simpler examples where we'll just talk about a single point. And for the people that are in the class, I'll try to slow down a little bit. Okay. So we have this statement right here. And let's take a, let's just say, f of x is going to equal the absolute value of x, okay? What is another way that we could define the absolute value of x? X if this can be defined in a couple ways. And now the graph of this guy, and that's going to end up on a YouTube video. Looks like this. Okay. So, right now the limit as x approaches 0 from the left is going to go towards 0. The limit as x approaches 0 from the right is going to go to 0. Okay. So since the limit from the left and the limit from the right agree with each other, the limit as x tends towards 0 of f of x is going to equal 0. And I actually define this in such a way that if I say x equals 0, well, the limit from the left and the limit from the right agree with each other. And so this function is continuous. You can take your hand, you can go da 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 da. Okay, I got to that point. if I approach from the right, yeah, I get to that point. And it equals the function value at that point. So this function is continuous at that point. All right? But is this function differentiable at that point? Okay? So if I'm saying, okay, if I was calculating the slope right here, I would have a positive one, but then I would have a negative one right here. Now, can I calculate the slope at that point? And remember, the slope as you, it is also a limit. All right? And so trying to calculate the slope as you approach from either direction of this guy, well, if you were trying to, let's say you were trying to graph f prime of x, okay? And so if I said, all right, yeah, I'm going to calculate what f prime of x is, that would be 1 if x is greater than 0, and negative 1 if x is less than 0. So, you're going to graph this thing. Okay, so I have a open dot here. And it would have a negative 1 right there. So your slope of the function off to the right is positive 1. Your slope of the function off to the left is negative 1. So considering what the slope is at that point, well, if you approach, and remember this is also a limit. The definition of a derivative is a limit. That's a little low on the screen. Or at least on the screen that's recording. All right? And so, differentiability is a limit. So, now, if I was approaching from the right, it looks like positive 1. If I'm approaching from the left, it looks like negative 1. These two limits don't agree from the right or the left. And so if I was going to try to calculate the slope at this point right here, there's no way to do it. Okay? So what we say for this problem, we're talking about now f of x equals the absolute value of x is continuous at x which equals 0, okay? But is not differentiable. So, differentiability is a stronger condition than continuity. So you can have something that's continuous. Yeah, sure, why not? Is it differentiable at that point? No, okay? And, well, on one of the extra assignments that I posted into your Blackboard, there's some word puzzles on there. And one belongs to Charles Hermite, who, it's a quote about lamentable plague of continuous functions, of functions that are continuous everywhere but differentiable nowhere. So why would Charles Hermite have been discussing a lamentable plague of functions that are continuous everywhere but differentiable nowhere? Well, this has to do with, you kind of think about the stock market, or things with random walk, okay? So if you had something that, let's say, try and draw like a little bit of a stock market picture. Okay, but let's say we zoomed in just like on this area right here. Okay, let's say we blew it up. And even as we zoomed into this picture, it's still squiggly. And even if we zoomed into, let's say, this part right here and we blew it up, well, it's still squiggly. And it doesn't matter how much we zoom in, we can't calculate the slope at any one of these points. And this actually has a relationship with something that's known as a fractal. So that if you zoom in on an object, the same type of object ends up appearing, then yeah, this is an example of something that it's continuous everywhere. I mean, you can keep your finger on that line and just like rock it back and forth insanely. And but if you try to calculate the slope at any point upon this line, no, you can't do it. Okay, so this is why differentiability is a much stronger concept than continuity, because you can have things that are continuous everywhere, but you can't have them being differentiable. Okay, and so what is another word for differentiability that is often used in mathematics? Smooth. So where something is smooth. Okay. And so what are we looking for when we're looking for things that are not differentiable? We're looking for cusps or angles or weird things like that. So normally when I give people tests, I actually just give them a graph and I say, tell me where this function is differentiable, and then tell me where this function is continuous. Okay, so let's start with that. Make it a little bit around. Okay, so let's say I gave y'all a graph. Solid dot right there. Let's say I go up, over, like that, and over. Let's just do this open dot right there. And let's call this 2. We'll call this -2. We'll call this 4. And why not? We'll call this -4. Okay. Now, we do have the concept of something being continuous from the right or continuous from the left. If it is an endpoint, so this endpoint is continuous because it's filled in, so we're going to use a bracket on that one. When it comes to differentiability, you're never going to use a bracket. Okay, in some later forms of math, there are some forms of analysis that talk about functions being differentiable at an endpoint, or even pseudo-differentiable, but that's way out of the realm of this class. So what I'm going to say for this class is just never use a bracket when talking about differentiability, but you can't use a bracket when talking about continuity. Okay? So the question that I would ask is, what is the interval of continuity? And by interval, I'm meaning the x values. And what is the interval of differentiability? Okay. And so let's begin with the interval of continuity. And so if I start right here. Well, this is open right here, so I'm not going to include that point. But if I put my finger right here, just right next to it, and I say, okay, I can put my finger there, I can put my finger there, and I have to pull up my finger on that point because there's an empty spot right there. But then I can continue down here. Okay. So the interval of continuity of this problem, that would be -4 all the way up till 2, and then union 2 all the way to 4. And 4 is an endpoint. And so since that endpoint is a solid filled end dot, we're going to put a bracket on that one. Okay. And so when I talk about the intervals of differentiability, okay, well, this is going to have a stronger condition to it. So this would be -4 to -2, then union -2 up to 0, and then union 0 to 2, and union 2 to 4. Okay. So at these points where we have these sharp corners, so if I try to calculate the slope at this point right here, well, it's positive on this end, and then all of a sudden it changes to being negative. So that is not a point of differentiability. And then for this point right here, well, if we're approaching that point from this direction, it looks like we have a negative slope, and then all of a sudden it changes to a positive slope. Right? And then when we get to that point right there, we'd say, well, that point is not even continuous. So if it's not continuous, then it's not going to be differentiable. Okay? So we're not going to include that point right there. And even if you try to calculate the slope at that point, it's got different slopes approaching in different directions. So you can see that there are a lot more points that are not differentiable versus points that are not continuous.